The objective of this video is to develop power loss expressions for semiconductor devices. So specifically, we're going to be talking about the MOSFETs and the diodes that make up our single-pole double-throw switch. And there are two loss sources. The losses can be divided into conduction losses and switching losses. Let's start by talking about conduction losses. These occur when the device is in the on state. For the diode, we can calculate conduction losses based on the equivalent circuit of our diode when it's conducting, which is a voltage source with a forward voltage diode drop, the diode's forward voltage drop, and a current flowing through it, ID. PC is equal to the forward voltage drop of the diode times the diode current, and this is the average diode current. And if you remember from our last video, we talked about how the forward voltage drop can actually be a function of the diode current based on the data sheet. But typically you pick the nominal condition and you calculate conduction losses in this manner. For the MOSFET, we can consider its equivalent circuit as being RDS on, so just a simple resistor between the drain and source. And flowing through RDS on is the MOSFET current. And it's useful to calculate this quantity in terms of RMS so that we can write the conduction losses as being the RMS current squared times RDS on. Next, we'll discuss switching losses. And switching losses are a bit more complicated. To discuss switching losses, we're going to consider the single-pole double-throw switch in this configuration. That's with a positive IP current going to a DC current source and a positive throw voltage. So the realization for this is the following: MOSFET and diode pair. And we're going to label the top throw current as ID, or the drain current of the MOSFET. So the MOSFET is turned on and off by a gate driver that applies a gate to source voltage through a gate resistance. And we're going to talk about gate drivers in more detail later, but it's important to note this for this discussion, that the gate driver can be modeled as an equivalent voltage source that applies a voltage to the gate of the MOSFET through a resistance. So there's both a physical resistor that we will place there, as well as the internal resistance of the MOSFET device. And we're going to consider this in two circumstances. The first is during turn on, and the second will be during turn off. When we go to turn this device on, we're in a state where the diode is conducting the total current of IL, and the MOSFET is completely off. And we can plot our IV characteristics of the MOSFET. And each of these lines corresponds to a different gate source voltage. So we can visualize the turn on process as having us start with the drain to source voltage being equal to the throw voltage, VT, and no current conducting. And as we turn the device on, it first must transition up this path towards some gate source voltage that corresponds to our output current, IL, because that is the current that must flow through the device when it's on, and then passing through this trajectory as we further increase the drain. So we're going to draw two graphs of the MOSFET terminal voltage and currents, and we'll label a couple times on these graphs. On the top graph, we're going to graph our gate to source voltage. And when we start off, we're going to assume that our MOSFET gate has 0 volts on it, and that the gate driver is trying to drive it to some nominal rated gate source voltage. And so initially when we turn the gate driver on, the gate driver goes to perhaps VGG, But charging the gate up involves charging up this RC network. So our equivalent circuit of our MOSFET with the gate resistor is as follows. We can talk about there being a capacitor between the gate and the drain. And a capacitor between the gate and the source. So the voltage rise waveform looks like the curve of charging up an RC network. And in the first interval here, we're rising from 0 volts to the threshold voltage of the device. And we'll call this time period TD on. This is the delay time before the device starts to turn on. The instant that we hit our threshold voltage, our MOSFET current starts to rise, our drain current starts to rise. So this is ID. And before any of this has happened, we can talk about the drain source voltage is fixed at our throw voltage. And as the drain current starts to rise, we're on this trajectory right here, which means that our drain source voltage remains fixed at VT. You can see this for a couple of reasons. One, the IV characteristics that we just described, but primarily due to the behavior of the circuit. So in this circuit, we have a diode and the MOSFET, and when the diode is conducting, it has to have 0 volts across it, or rather it's the forward voltage drop, so it has about 1 volt across it, which means that the MOSFET must carry the remainder of the throw voltage. So as long as any of our output current, as long as any of IL is coming through the diode remains at 1 volt, and the MOSFET has to block the remainder of the throw voltage. So at this next time over here, our drain volt current now matches our load current, and we are at point B at this time right here, where our drain current is matching our load current. And the MOSFET drain source voltage can now start to decrease. So our MOSFET drain to source voltage, it turns out, is going to ramp down. And while the drain source voltage is ramping down, the gate source voltage actually remains fixed exactly at the gate source voltage required to obtain IL. So exactly at this point B on the top. So what's happening during this interval? Why do we observe this odd behavior where our gate source voltage becomes fixed while our drain source voltage collapses? So in order for the drain source voltage to decrease, we can see that we have to change the charge on our gate to drain capacitor. So in this initial interval, the drain source voltage is fixed, and all of our gate current is going into charging the gate to source capacitance. In this interval, our gate source voltage is fixed, and all of our gate current is going into charging the gate to drain capacitance. And you can actually analyze this based on the equivalent circuit that we've sketched on the side here, where we note that in general for a capacitor, we have this differential equation where the derivative of our voltage is equal to our capacitor current divided by our capacitance. And during this second interval, I'll call this interval 2 and this interval 1. So during 2, the change in our drain to gate voltage can be expressed as the current going into that capacitance divided by the gate to drain capacitance. So the amount of time it takes for the voltage to fall is related to how quickly we can charge that capacitance or discharge it. So let's label some intervals here. This interval right here is called TRI, or the current rise time. This interval right here is called TFV, or the voltage fall time. When our drain to source voltage finally falls in this interval out here, it becomes equal to RDS on times IL, just the voltage drop across the equivalent resistance. So what does this mean for losses? Well, the power losses are the energy that's dissipated is the area underneath this curve here. And we can draw another graph below which labels our power losses. And clearly the peak of this triangle is going to be the product of these two curves up above. So it is going to be VT times IL. And the width of it is dependent on the current rise time and the voltage fall time. So we can get an expression for the average turn on power as being the area of this triangle divided by the period of the triangle. So at this point, this is the integral of that triangle, and this is the total energy it takes to turn the device on. And if we divide this by our switching period, the frequency that this occurs at, we get the power losses, the average power loss. So this is the power loss due to turning the device on. Let's now talk about turning the device off. So during the turn-off interval, we can maintain our same IV characteristics, and instead we'll note that we're going to be transitioning along this trajectory. And we'll sketch our voltage and current waveforms again. Our gate source voltage at this point starts at the gate driver's VGG value. That's the DC value that the gate driver drives the gate up to when it's turned on. And it will then decay down to the gate source voltage required to maintain the load current. And that corresponds to point B on our IV characteristics. The gate source voltage then becomes fixed again, similar to turn on. This is when our gate drain capacitance is charging back up to allow the drain to source voltage to increase. And then it continues its RC decay, where this corresponds to our threshold voltage. Similarly, we can sketch our current. So our drain current starts off as being our load current, and it maintains this value until our gate source voltage drops below the gate source voltage that can support it, and our device then shuts off. Our drain source voltage starts off at 0 volts, or rather the voltage drop across RDS on. And in this interval here, it rises up to the throw voltage, which it stays at. And finally, we can use these curves to calculate the power dissipation in our device, which again looks like a triangle. So again, we're multiplying this area. And we can label these time intervals. This first interval is our delay time before it turns off, so TD off. This next interval is our voltage rise time. and then our current fall time. So we can now add to our loss expression the power loss terms related to the MOSFET turnoff as being this area underneath this curve is the energy again, and if you multiply that by the switching period, you get the average power. We now have an expression for the power loss due to switching of the MOSFET, both during the turn-on event and during the turn-off event. Let's add to our waveforms a diagram of the diode current. So going up to our schematic, we've labeled this diode current as being the current through throw 2. And in the turn-on interval, we start off with the diode being completely on and conducting, so IT2 is equal to IL. And as our MOSFET begins to turn on, as the drain current ramps up, this current ramps down correspondingly until it's off. So remember, as long as the diode is conducting, the entire voltage of the throw has to appear across the MOSFET, because the diode, by definition, can only have the forward voltage drop that we see in the data sheet. So we can add to this a graph of the diode voltage drop. So we start off with the diode having the forward voltage as indicated in the data sheet corresponding to the current IL, and this remains at that value until our drain source voltage starts to drop, and then this increases to block the entire throw voltage. Similarly, in the turn-off interval, when the MOSFET is turning off, the diode is initially not conducting. So diode has zero current initially, and it stays this way until the drain current of the MOSFET starts to decrease, and then the diode has to conduct the entire load current. The voltage mirrors that of the drain source voltage of the MOSFET. So initially, the diode has the complete drain source voltage across it, and then it decreases as the drain source voltage of the MOSFET increases until we get again to VD of IL. In our analysis so far, we've been considering our diodes to be nearly ideal. We've neglected any transient effects of the diode. We pretend that it turns on and off exactly when we want it to be. However, this is not actually the case, as real diodes suffer from something known as reverse recovery. So we'll again consider the same switch realization with a MOSFET on the top and a diode on the bottom, only now we're going to notice that when we go to turn our diode off, we have to establish a depletion region which requires charge to be swept out and established across the junction of our diode. So our junction requires our junction effectively has a capacitance across it, and this capacitance needs to be charged or discharged, which changes the behavior of our switching power pole during turn off, or during turn on rather. So when the diode turns off, we get new behavior. So we're going to say the diode turn off. We can observe this by simply plotting the diode current. So again, we've labeled the current through the diode as IT2. And IT2 starts out at the load current, and then it goes negative. The difference here is that IT2 now goes negative. And this region right here where it's gone negative is the result of needing to establish the charge in the PN junction. So we can talk about this region as having an effective charge that we need to establish, and we can say we can relate it to a couple of quantities which are specified in the data sheet. Now, one is a reverse recovery current, and the other is the reverse recovery time. So we're going to denote this as being we're going to break this into two time intervals, time interval A and time interval B, and together they make up the entire TRR time, reverse recovery time, which is specified on a data sheet. And so the total charge, or the area underneath this curve, is approximately 1/2 IRR times TRR. And this has the effect of increasing the MOSFET losses. Why is this? Well, let's redraw our MOSFET turn on. And we're going to consider this for the case where TB is assumed to be 0. And so if we plot our MOSFET drain current, is that it will increase the value that it normally would have, which is IL, but it's going to keep going. From IL, it's going to keep on increasing until it gets to the value IL plus IRR. And then it will suddenly decrease and return to IL. Meanwhile, our voltage is going to look the same as it previously did. That is, we'll start off at VDS equal to VT, and then it will decrease. So if we plot our power losses down below, we'll notice that at first we start out with the same curve, but this curve now extends to include the new region due to reverse recovery. So this first region is the same, and then we have the new reverse recovery region, which is here. And then suddenly we jump back down to having the same first region again over here. So our current rise time is the same as it was before, but now we get this extra reverse recovery time, and then our voltage fall time is the same as it was before. So we can now write an updated switching loss expression during MOSFET turn on, which adds the new area due to our reverse recovery. So again, that new area is this region right here. So as before, we start talking about the area of this first triangle, which we'll now consider to be this entire area, with an updated time of TRI plus TRR, and then add in our remaining region over here. And then of course we have to add in the losses due to MOSFET turn off that we previously calculated. So by adding the reverse recovery characteristics of the diode, we added this term and this term to our loss expression. And in some cases this can be very significant. There's an example in your textbook where the reverse recovery losses actually double the normal switching losses of the MOSFET. So you have to know whether to consider this or not for a given design. You have to look at the data sheet of your MOSFET. Some of the newer, some of the newer diodes that use silicon carbide claim to actually have no reverse recovery phenomenon or no observable reverse recovery phenomenon, while some of the legacy diodes or the conventional product can have very significant reverse recovery. So we're now in a position to make calculations for the entirety of the losses that are occurring within our semiconductor devices. That's the conduction losses of the MOSFET and the diode, and the switching losses of the MOSFET.